Normandy, July 1944. A German reconnaissance patrol, elements of the Panzer-Lehr Division, stumbled upon a derelict American M4A1 Sherman tank, its tracks mangled by a hidden mine, its crew long gone. This unexpected prize, lying abandoned in a shallow ditch near a shelled farmhouse, represented a rare opportunity to directly assess the enemy's primary armored fighting vehicle, a machine whose true capabilities remained largely a matter of rumor and scattered intelligence reports. For weeks, the sheer numbers of these American tanks had been a growing concern, their ubiquitous presence on the battlefield hinting at an industrial capacity that Germany could not match. Oberleutnant Klaus Richter, a tank design engineer seconded to Panzer-Lehr for field evaluation, received the order to secure and examine the Sherman just after 0400 hours. His initial assessment, conducted under the pale pre-dawn light, noted the vehicle's compact silhouette and somewhat crude welded construction, a stark contrast to the precise, interlocking armor plates of the Panther or Tiger. He had anticipated a formidable machine, a testament to American ingenuity, yet the exterior suggested a utilitarian, almost mass-produced quality, lacking the refined aggression of German designs. The Sherman, an M4A1 variant, bore the marks of its last engagement: scorched paint near the engine deck, a shattered periscope, and a gaping hole in its right track assembly. Richter's team quickly established a perimeter, then began a preliminary inspection of the hull. The cast armor, while appearing thick, lacked the sloped glacis of newer German designs, presenting a more direct target to anti-tank rounds. He ran a gloved hand over the rough texture of the casting, noting the apparent lack of sophisticated metallurgy evident in the finish. Inside the turret, the 75mm M3 main gun seemed adequate, though Richter knew it was outmatched by the long 7.5 centimeters KWK-42 L70 of the Panther. The cramped fighting compartment, designed for a 5-man crew, felt less spacious than anticipated, suggesting compromises in ergonomics for the sake of overall vehicle dimensions. The radio equipment, a CCR 508, was robust and clearly designed for ease of use, indicating a focus on battlefield communication that was often a secondary consideration in German tank development. Richter's team worked methodically, cataloging every visible detail. The suspension, a vertical volute spring suspension (VVSS) system, was externally mounted and appeared vulnerable to artillery and small arms fire, a design choice that puzzled him given the importance of mobility in armored warfare. The rubber block tracks, while wide, seemed less durable than the all-steel tracks common on German tanks, raising questions about their longevity in prolonged combat. The engine compartment, once accessed, revealed a radial aircraft engine, the Continental R975C1, a surprising choice for a ground vehicle. Its 400 horsepower output was respectable for the Sherman's 30-ton weight, providing a decent power-to-weight ratio. However, the use of a gasoline engine, rather than the more fuel-efficient and less flammable diesel engines favored by some nations, immediately struck Richter as a significant vulnerability, a potential fire trap in the event of a penetrating hit. The initial impression was one of functional simplicity, a vehicle built for rapid production rather than overwhelming individual combat prowess. Richter recorded his observations, noting the apparent compromises in armor, armament, and engine type. He understood the strategic implications of such a design philosophy, but the tactical reality of facing these machines on the battlefield still felt distant, almost theoretical, as he meticulously documented the details of this captured enemy tank. The captured M4A1 Sherman, still bearing the fresh scars of its last engagement, was transported under heavy guard to a designated testing ground within the Kummersdorf Proving Complex. Its arrival marked the culmination of an urgent directive from Army Ordnance, eager to dissect the enemy's primary medium tank. Engineers and ballistics experts, many veterans of the Panzer program, began their meticulous examination. Initial observations focused on the hull's cast construction, a stark contrast to the welded and interlocking plate designs prevalent in German tank production. The rounded contours of the casting were immediately noted for their inherent shot deflection properties, a design choice that simplified manufacturing but presented a formidable challenge to incoming projectiles. Detailed measurements confirmed an average frontal armor thickness of 51 millimeters, tapering to 38 millimeters on the sides. The suspension system, specifically the vertical volute spring suspension (VVSS), drew considerable attention. Its robust, modular design, with each bogie assembly containing 2 road wheels and a return roller, allowed for relatively easy field maintenance and replacement. Engineers noted the large rubber tires on the road wheels, a feature that contributed to a smoother ride but raised concerns about vulnerability to sustained small arms fire and fragmentation. Access panels and engine deck plating were systematically removed, revealing the Continental R975C1 radial aircraft engine. This air-cooled, 9-cylinder power plant, rated at 400 horsepower, was a surprising choice for a tank. Yet its widespread availability from aircraft production lines clearly facilitated rapid manufacturing. The power-to-weight ratio, calculated at approximately 12.5 horsepower per metric ton, suggested a tank capable of respectable mobility. The transmission and final drive assembly, a single integrated unit mounted at the front of the hull, was thoroughly inspected. Its placement, while simplifying maintenance, also meant that a direct hit to the front glacis could disable both the drive and the engine, a significant tactical vulnerability. The 5-speed constant mesh gearbox, though conventional, was robustly engineered for reliability under combat conditions. Inside the turret, the 75mm M3 gun was the primary focus. Ballistics specialists measured its barrel length at 37.5 calibers, a relatively short weapon compared to the high-velocity 7.5 centimeter KWK-40 L-48 mounted on the Panzer IV Ausf G. The M3's muzzle velocity, documented in American ordnance manuals as 619 meters per second, with standard M72 armor-piercing shot, indicated a projectile capable of penetrating approximately 76 millimeters of vertical armor at 500 meters. The turret traverse mechanism, a hydraulic system, allowed for a rapid 360-degree rotation in approximately 15 seconds. This speed, combined with the gun's vertical stabilization system, was a distinct advantage in engaging moving targets, a capability largely absent from most contemporary German designs. The crew ergonomics, with ample space for the gunner and loader, were also noted, suggesting a design prioritized for combat efficiency. Ample ammunition storage, with 97 rounds for the main gun, was distributed throughout the hull, a design choice that would later prove problematic in terms of survivability. The internal layout, though somewhat cramped by German standards, was functional and logically arranged, reflecting a design philosophy focused on ease of operation rather than absolute protection. The manufacturing techniques observed throughout the Sherman spoke volumes. The extensive use of casting, standardized components, and mass-produced subassemblies indicated an industrial capacity and a design philosophy geared towards rapid, large-scale production. This was a tank designed to be built in vast numbers, a stark contrast to the often bespoke, labor-intensive production of German heavy armor. Damage reports from the Easter, in front, detailing the attrition rates of German tanks, had already underscored the need for increased production. The Sherman's design, however, suggested a different scale of industrial mobilization, one that fundamentally altered the quantitative balance of armored warfare. Recommendation: immediate analysis of American industrial output capabilities. Kummersdorf Proving Grounds, late 1943. The captured M4A2 Sherman, its olive drab paint now crudely overpainted with German crosses, was subjected to an exhaustive series of performance trials. Engineers from Wehrmacht 6, the Waffenamt's testing department for armored vehicles, meticulously documented every aspect of its operation, from engine response to track articulation. Their initial objective was to understand the enemy's capabilities, but a more profound realization would soon emerge. The Sherman's 370 horsepower General Motors 6046 twin diesel engine, a compact and readily available power plant, demonstrated remarkable reliability during sustained high-speed runs. Unlike the complex and often temperamental Maybach engines powering German heavy tanks, the GM unit started consistently in cold weather and maintained its performance across varied terrain. Fuel consumption logs indicated an operational range of approximately 160 kilometers on paved roads, a practical advantage for rapid deployment. Mobility tests revealed the Sherman's superior cross-country performance compared to its German counterparts. Its vertical volute spring suspension (VVSS) system, while appearing less sophisticated than the interleaved road wheels of a Panther, proved exceptionally durable and allowed for higher speeds over uneven ground. Test drivers accustomed to the jarring ride of a Panzer III or IV noted the Sherman's relatively smooth traversal of shell-cratered fields and muddy tracks, a significant factor in crew fatigue and combat effectiveness. The turret traverse mechanism, a hydraulic system, provided a full 360-degree rotation in approximately 15 seconds, a speed that impressed the German observers. This rapid target acquisition capability contrasted sharply with the slower, often hand-cranked turrets of many German tanks, offering a distinct advantage in dynamic engagements. The 75mm M3 main gun, though known to be less potent than the German 7.5 cm Quak 40, was found to have a high rate of fire, capable of delivering up to 20 rounds per minute under optimal conditions. A detailed examination of the transmission and final drives revealed a robust and relatively simple design, facilitating easier maintenance and repair in the field. The German engineers noted the extensive use of standardized components, a clear departure from the bespoke, often over-engineered parts found in their own designs. This modularity translated directly into faster production times and simplified logistics, a stark contrast to the chronic spare parts shortages plaguing the Wehrmacht's armored divisions. Armor penetration tests, however, confirmed the Sherman's primary vulnerability. While the sloped frontal glacis plate offered reasonable protection against smaller caliber anti-tank rounds, the vertical side armor and rear plating were easily defeated by the 7.5 cm Quak 40 and 8.8 cm Quak 36 guns at typical engagement ranges. The ammunition stowage, they improved from earlier designs, still presented a significant risk of catastrophic internal explosion upon penetration, a flaw that would become tragically familiar to Allied crews. The internal layout of the Sherman, with its spacious fighting compartment, was deemed highly ergonomic. Crew access and egress were straightforward, and the placement of controls was intuitive. This design philosophy, prioritizing crew comfort and operational efficiency, stood in marked contrast to the often cramped and complex interiors of German tanks, where the demands of armor and firepower frequently dictated internal arrangements. The report noted, crew comfort directly impacts combat endurance. Production logs, later acquired through intelligence channels, revealed that American factories were capable of producing thousands of Shermans per month, a rate that dwarfed German output. In 1943 alone, over 8,000 M4 variants were delivered, a testament to the American industrial base's capacity for mass production. This sheer volume, combined with the tank's operational reliability, presented a strategic challenge far greater than any individual technical superiority. The Kummersdorf trials thus painted a complex picture. The Sherman was not a tank of overwhelming individual technical prowess, but rather a robust, reliable, and highly mobile platform designed for mass production and effective combined arms operations. Its strengths lay not in individual specifications, but in its systemic advantages, its ease of maintenance, and its sheer numbers, a realization that began to chip away at the German perception of their own armored invincibility. The analysis of the M4A2's 75mm M3 main gun revealed a weapon of surprising versatility. German ballistic reports, compiled from firing tests against captured Panzer III and IV hulls, indicated consistent penetration of 80mm of face-hardened armor at 500 meters using standard APCBC rounds. While not matching the raw kinetic energy of the KWK-40 L-48 on the Panzer IV Ausfig G, the M3's muzzle velocity of 619 meters per second was sufficient to defeat the frontal armor of most German medium tanks encountered in North Africa and early Italy, particularly at typical engagement ranges. Examination of the turret traverse mechanism, a hydraulic system, showed a rapid and smooth 360-degree rotation in approximately 15 seconds. This speed, significantly faster than the manual traverse on most German tanks, offered a critical advantage in target acquisition and engagement, particularly in dynamic combat situations. The gunner's periscopic sight, though simpler than the sophisticated optics found on later German designs, provided adequate magnification and a wide field of view, contributing to the tank's quick reaction time. The armor scheme, initially dismissed as inadequate, demonstrated a pragmatic approach to protection. German metallurgical reports confirmed the Sherman's cast homogeneous armor, while not as hard as rolled plate, offered good resistance to shattering and spalling. The sloped glacis plate, angled at 47 degrees from the vertical, effectively increased the line-of-sight thickness to over 100 millimeters against horizontal impacts, a detail often overlooked in static assessments. This design philosophy prioritized a balance of protection and manufacturing ease. Mobility tests on the seized M4A2 highlighted another unexpected strength. The twin General Motors 671 diesel engines, producing 375 horsepower, propelled the 32-ton vehicle to a top road speed of 48 kilometers per hour. Cross-country performance, aided by the vertical volute spring suspension, VVSS, and wide tracks, proved superior to many German designs, particularly in soft ground conditions. The transmission, a 5-speed manual with a high-low range, allowed for precise control and efficient power delivery, contributing to the tank's agility. The internal layout, while compact, was designed for operational efficiency. The crew positions, particularly the driver and co-driver, offered good visibility and relatively comfortable conditions for extended operations. Ammunition stowage, though a known vulnerability in earlier Sherman variants, was organized for quick access, and the overall ergonomics suggested a vehicle built for sustained combat, not just individual engagements. The ease of maintenance, observed during field inspections, further underscored its practical design. Production logs, captured from American supply depots, revealed the sheer scale of Sherman manufacturing. By late 1943, American factories were producing over 1,500 N4 tanks per month, a volume unmatched by German industry. This industrial capacity meant that even if individual Sherman tanks were theoretically inferior to the latest German designs, their overwhelming numbers would inevitably tip the balance of attrition. The engineers understood that a single superior tank could be lost, but 1,000 adequate tanks would always prevail. The interrogation files from late 1943, compiled by Abteilung Fremde Heer West, contained a recurring theme: the sheer volume of American materiel. Captured engineers, their initial enthusiasm for the M4's technical details, tempered by broader strategic assessments, began to articulate a growing dread. They had seen the tank, understood its design, and now the arithmetic of its deployment began to sink in. Production logs from the Detroit arsenal, later obtained through intelligence channels, detailed the output. By the end of 1942, over 10,000 M4 Sherman tanks had rolled off assembly lines. The following year, 1943, saw that number surge to nearly 23,000 units. This was not a trickle. It was a deluge, a manufacturing tsunami that dwarfed German efforts. In comparison, German tank production, while focused on increasingly sophisticated designs like the Panther and Tiger, remained profoundly limited. The Panther, a direct response to Soviet T-34s and a tank superior to the M4 in many respects, saw only 1,768 units produced in 1943. The formidable Tiger I, a heavy tank designed for breakthrough and anti-tank roles, managed a mere 647 units in the same period. The disparity was not just in quantity, but in the underlying industrial philosophy. German manufacturing, even under Albert Speer's rationalization efforts, retained elements of bespoke craftsmanship, prioritizing engineering perfection and modularity for future upgrades. American production, by contrast, embraced standardization and mass assembly, often sacrificing individual component elegance for sheer rate of output. This difference in approach translated directly into battlefield availability. While a single Tiger might statistically account for several Shermans, the cumulative effect of hundreds, then thousands, of American tanks meant that numerical superiority would increasingly overwhelm tactical advantage. The captured M4, once a trophy, became a stark illustration of a war being fought on fundamentally different industrial scales. The reports filtering up to the Oberkommando des Heeres painted a grim picture. German forces, even with their superior individual tank designs, would face an enemy capable of absorbing losses and continually reinforcing their lines with new equipment. The M4, in its ubiquity, represented not just a tank, but a symbol of an industrial capacity that Germany could not hope to match. The captured Sherman, now meticulously documented and disassembled, became a stark, tangible representation of the chasm between two warring industrial philosophies. German engineers, poring over the detailed schematics and material analyses, confronted the reality of a production model designed for mass output and battlefield resilience, not individual technological superiority. The American approach prioritized standardization, ease of manufacture, and sheer volume, a strategy that was becoming increasingly evident in the numerical advantage their forces held across every front. Production logs from the U.S. War Department, reviewed by German intelligence, revealed an astonishing rate of output. By late 1943, the Ford Motor Company alone was producing M4 Sherman hulls at a rate that would soon exceed 1,000 units per month, a figure that dwarfed the combined monthly output of all German medium tanks. The M4's modular design, with its interchangeable components and simplified assembly, allowed for this unprecedented scale, a stark contrast to the bespoke, labor-intensive construction of a Panther or Tiger. The metallurgical reports further underscored this disparity. While German armor plates often boasted superior hardness and ballistic properties in individual tests, the consistency and availability of these high-grade alloys were increasingly problematic for the Reich. The Sherman's armor, though generally thinner and less dense, was produced with remarkable uniformity from readily available steel, a testament to an industrial base unburdened by critical material shortages and strategic bombing. This difference in material supply chains directly impacted the ability to field tanks in sufficient numbers. The internal layout of the Sherman, with its relatively generous crew space and well-ventilated engine compartment, reflected a design philosophy that considered maintenance and crew comfort alongside combat effectiveness. German tanks, while often boasting more powerful main guns and thicker frontal armor, frequently sacrificed ergonomics and ease of field repair in pursuit of maximum combat performance. This meant that a damaged Sherman could often be returned to service far more quickly and with fewer specialized tools than its German counterpart. The strategic implications of these findings were profound. The German High Command had consistently pushed for increasingly complex and powerful designs, believing that technological superiority could offset numerical disadvantage. The Sherman, however, demonstrated that a simpler, more robust, and infinitely more numerous design could achieve overwhelming strategic advantage through attrition and sheer presence. The American tank was not just a fighting machine. It was a symbol of an industrial might that Germany could no longer hope to match. The final assessment, circulated among the panzer divisions, acknowledged the Sherman's limitations against the latest German heavy tanks, but emphasized its overwhelming strategic value. The report concluded that the M4 represented a formidable and adaptable weapon system, perfectly suited to the American doctrine of combined arms and rapid exploitation. Its very ubiquity was its strength, a relentless tide against which even the most advanced German armor would eventually be overwhelmed. Berlin, late 1943. The reports from the captured M4 Sherman, meticulously compiled by the Waffenamt's technical committees, began their ascent through the labyrinthine command structures. Each page, detailing armor composition, engine performance, and manufacturing techniques, offered a stark quantitative measure of the widening chasm between German ambition and industrial reality. The initial triumph of securing an intact enemy tank had curdled into a bitter accounting. The analysis of the Sherman's Ford GAA engine, a V8 specifically designed for tank use, revealed a power plant that delivered 450 horsepower from a compact, easily serviceable unit. German production logs showed that comparable power outputs in their own tanks often required more complex, less reliable Maybach engines, frequently repurposed from automotive designs. Demanding greater manufacturing precision and more specialized materials, the American engine, designed for mass production, used simpler castings and fewer exotic alloys. Further examination of the Sherman's hull, particularly its cast sections, underscored a fundamental divergence in industrial philosophy. While German engineers meticulously welded complex, rolled homogeneous armor plates, the Americans had embraced large-scale casting, a process that, while potentially yielding less optimal metallurgical properties in some instances, dramatically reduced manufacturing time and labor. A single cast hull could be produced in a fraction of the hours required for a welded equivalent, a critical factor when facing an enemy whose industrial output dwarfed their own. The internal layout and ergonomic considerations within the Sherman also spoke volumes. The spacious fighting compartment, the provision for a dedicated yoder, and the relatively straightforward maintenance access points reflected a design ethos focused on crew efficiency and battlefield sustainability. German designs, often cramped and complex, prioritized protection and firepower above all else, sometimes at the expense of the very crews who operated them. This difference was not merely one of comfort, but of combat effectiveness and crew morale over extended operations. Production figures, gleaned from intelligence intercepts and prisoner interrogations, painted the most damning picture. While German factories struggled to produce a few hundred Panther tanks per month, each a marvel of engineering but a drain on resources, American plants were churning out thousands of Shermans. The sheer volume, coupled with the relative ease of repair and standardization of parts, meant that even if individual German tanks were superior on paper, they were being overwhelmed by a relentless tide of material. The cumulative effect of these reports was a growing sense of inevitability within the highest echelons of the Wehrmacht and the armaments ministry. The meticulous German engineering once a source of immense pride, was now revealed as a double-edged sword, producing exquisite but labor-intensive machines that could not compete with the enemy's industrial might. The captured Sherman was not just a tank, it was a physical manifestation of an unbridgeable production gap. The realization settled that the war was becoming less about individual tank quality and more about the scale of industrial output. Germany, with its finite resources and strategic bombing campaigns beginning to bite, could not hope to match the Allied capacity for mass production. The Sherman, in its simplicity and abundance, represented a strategic threat far greater than its individual combat capabilities suggested. The path ahead, already fraught with tactical difficulties, now seemed industrially insurmountable. The reports from the Kummersdorf Proving Grounds, compiled in late 1943, circulated through the highest echelons of the Heereswaffenamt, detailing the Sherman's performance and design. These documents, marked Geheim, outlined the American tank's surprising blend of reliability and combat effectiveness, particularly its automotive resilience and ease of maintenance in the field. The engineers' findings underscored a critical divergence in industrial philosophy, where German design prioritized individual, often bespoke, technological superiority in each component, while American industry focused on mass-producible, robust systems. Comparative production logs from the Reichsministerium für Rüstung und Kriegsproduktion and Allied intelligence estimates, later confirmed by post-war analyses, reveal the stark scale of this difference. In 1943, German factories, despite their technological prowess, produced approximately 4,200 Panzers of all types. During that same year, American factories rolled out over 20,000 Sherman tanks, a rate of nearly 5 to 1. This quantitative disparity was not merely a matter of numbers. It represented a fundamental difference in industrial capacity and strategic outlook. The captured Sherman, now a subject of intense scrutiny, became a physical manifestation of this burgeoning imbalance. Its simple, welded hull construction, while offering less ballistic protection than the interlocking plates of a Panther, allowed for rapid assembly by semi-skilled labor. The interchangeable parts, standardized across thousands of units, facilitated a logistics chain of unprecedented efficiency, a concept largely foreign to the bespoke nature of German tank production, where even minor components often required hand-fitting. Engineers at Henschel and MAN, reviewing the Sherman's design, noted the commonality of its Ford GAA engine,